In this video, we'll be talking about section 5.5, which is the last section in the Calc 1 course, and we'll be discussing how to use substitution in order to integrate both definite and indefinite integrals. So the concept of needing to use substitution to integrate is based on the fact that we have to use the chain rule sometimes when we have a composition of two functions and we're trying to take its derivative. So here I have an example of a function where we would use the chain rule in order to find the derivative. So let's just think about how that would go. So finding the derivative, I would use the power rule. So first of all, that 10 that's divided on the bottom, I might want to factor that out. It might just help us better see what we have. So if I factor out that 10, I'm going to find the derivative of this piece right here by doing the power rule. 10 times x plus 10 to the 9th times the derivative of what's inside, which in this case is 1, and the derivative of a constant 5 is 0. So in the end, I would get x plus 10 to the 9th. So what we're going to take a look at is how to do the opposite. How to take the integral of that expression with respect to x. So because we have to use the chain rule to find the derivative, it makes the integration much more complicated. So what we're going to do here is we're going to let u be x plus 10, which is the inner function. And if we find du, the derivative of x is 1, and the derivative of 10 is 0, and we need to multiply that with respect to x, or multiply that by dx. So what I'm going to do is I'm going to, instead of integrating this composition of two functions, something added to a variable and then raised to a power, I'm going to simplify it by integrating it with respect to u instead. So because I let x plus 10 equal u, now what I'm integrating is u to the 9th, and then dx is equal to du. So I can substitute everything I have in terms of u. Now let's integrate. So I'm integrating with respect to u, and all I have to do is use the power rule. Whoops. Sorry, that's supposed to say u to the 10th. Let me get rid of that. Okay, much better. So u to the 10th over 10. So we're just using a really easy power rule to integrate that u function, and then of course we have to add a constant because it's an indefinite integral. So now that I've integrated in terms of u, let's figure out then what the function would be if I substitute x back into it. So remember, u was equal to x plus 10, and there I have my antiderivative. Okay, so let's just remember that in the very beginning here, I started with that same function. Aside from a constant, I took its derivative and I got x plus 10 to the 9th. Then down here I did the opposite. I integrated x plus 10 to the 9th, and I got this same original function that I started with. Originally we had plus 5, here we have plus c. Remember that that constant is arbitrary. So that's a quick example of how to use u substitution to integrate more complicated compositions of functions. Let me summarize what I did so that we can apply it to any particular integration. So first of all, this method is useful when we're integrating a composition of two functions. And we want to look for the innermost piece and set that equal to u. And so typically g of x, your inside function. That is definitely the most difficult part of this process, is figuring out what to let u equal. And it takes a little time and a little bit of practice. And then, of course, a little bit of forethought. Because instead of, let me rephrase that, you're not just substituting in this function and letting it become u. You also need to substitute the d of x, or dx, I should say. So if you find the derivative of u, you're going to find the derivative of g and multiply it by dx. So you're also going to be making a substitution for dx as well. And if you select a u where its derivative is something that also appears in the integrand, then you're in good shape. Now, you'll see in a second, in an example that I do, that this may differ by a constant multiple. So in other words, when you find du, you might not see the exact expression g prime of x dx in the integrand, but it might be twice as much as that, or 1/2 of that, or some constant multiple of that, and that's still going to work out for you. Okay, next what we're going to do is we're going to substitute u and du so that we are integrating some form of that. It might be u to the 10th, like we had earlier, or u to the 9th, I should say. It might be the natural log of u, but you're integrating something that has u's in it. Once you do that, once you integrate, then you're going to resubstitute the original variable back into the problem. So again, here we're integrating with respect to u, and so in the end we have to put the x's back in order to find the final result. Okay, there is one more thing to consider, and I'm going to change the page here to talk about that. And so this is really step number 5, and this happens only when you have a definite integral. So remember, for definite integrals, that you're integrating over an interval from a to b. So as far as the variable x is concerned, your interval is a to b. Well, if you change that to a u variable, then you change your limits of integration. And so you do need to find your new lower limit and your new upper limit with respect to u. And then when you do that, you don't have any need to resubstitute. You're switching every part of this expression over into a u form, and you're going to use the fundamental theorem of calculus. So you don't need to resubstitute there as long as you do a change of variables. Okay, so I will get to an example of definite integration in a moment, but let me do another indefinite example. So let's say I'm going to integrate x times e to the x squared with respect to x. And again, it's an indefinite integral. So the first thing that we want to pick or we want to do is select u. So let's let u equal to some part of this composition of functions. Here, this is actually an even more complex integral because we have a product of two functions as well as a composition of one function plugged inside of another. So it is always best to try the innermost function of the composition first. So in that case, x squared would be the g of x, the innermost function in my composition. Now, let's find du and see if that's something that we can easily substitute in this problem. So the derivative of x squared is 2x dx. Okay, so that's pretty close. This is going to become e to the u. And then we're also going to need to get rid of this x and this dx. So what we have here is that du equals 2 times x dx. And we are differing by a constant multiple, which is okay. So all we need to do is divide both sides by 2. And we'll have 1/2 du equals x dx. So now when we substitute, instead of just doing a direct substitution, x dx becomes du. Instead, it's going to become 1/2 du. Alright, so let's plug everything in and completely change the variables of this problem. So once again, e to the x squared is e to the u, and then x dx, remember we had to divide, x dx is equivalent to 1/2 du. So that is what we're going to integrate. Now you can pull that constant multiple out in the front. This is one of the easiest integrations you can do, e to a power, because the derivative of it is itself, which means the antiderivative of it is also itself. So the antiderivative of e to the u is e to the u. Multiply it by your constant multiple. Add c. Alright, so this is the antiderivative with respect to u. Now let's resubstitute so that we get our x's back. So what was it that we let u equal? We let u equal x squared. Plug that back in, and we have 1/2 e to the x squared plus c. Now this might be a great time to pause the video and actually check to see that we've done this correctly. So if we've done this correctly, when we take the derivative of our answer, we should get x e to the x squared, which is what we integrated to begin with. So again, might be a good time to pause and make sure that this does check and that we did our integration correctly.